this lesson we're going to look at sample proportions in particular. Recall the Reese's Pieces activity in an earlier lesson, where we simulated the proportion of orange candies. We saw the effect on the center, shape, and spread of the distribution. What we saw was we could approximate the mean population proportion, P, with the sample proportion, or mu sub P hat. We also saw that as we increased the number of candies in, we decreased the variability, that is, the standard deviation. We also saw that the shape was very close to normal if the number of candies wasn't too small, nor was the probability too small or too large. More on this in a moment. So I want to summarize the sampling distribution of P hat. So if we take a simple random sample from a large population, then the mean of the sampling distribution is P. The standard deviation, sigma sub P hat, is the square root of P times 1 minus P all over N. We sometimes will, just for notational purposes, say that Q is 1 minus P. And that allows us to write this in a little more compact form, the square root of PQ over N. And finally, the sampling distribution of P hat will become close to normal as the sample size increases. We saw that. In particular, there are two conditions that need to be met. When N times P is greater than or equal to 10, and N times Q is greater than or equal to 10. Also note that since we generally sample without replacement, in order to assume independence, the sample size must be less than 10% of the population. So where did the standard deviation of the sample proportion P hat come from? Let's recall the binomial standard deviation. Sigma sub x equals the square root of NP times 1 minus P. This also could have been summarized as NPQ. Let's look at a concrete example. I think this will make sense. Suppose the probability of a particular basketball player making a free throw is 0.8, P equals 0.8. If he shoots 10 free throws, what's the mean number of free throws? This is also the expected number of free throws. So we simply multiply N times P. We expect him to get about 8 of these free throws made. So the mean proportion, what do? We simply divide that by 10, N. So symbolically, we take that mean sample proportion, N times P, and divide it by N, and we get P. No surprise there. Let's look at the standard deviation. If we looked at the binomial, again, we say N times P times 1 minus P, so this would be 10 times 0.8 times 0.2. This is about 1.26. If I wanted to convert that to proportion, all I do is divide by 10. And symbolically, what happens is I take that and divide it by N, and we have to do a little bit of an algebra move here, where when we divide by N, this is kind of, you can think of this as N to the 1/2. When we do that, it ends up coming downstairs, and we can again write it the way it was shown originally. PQ over N, the square root of all that. Example 1. Suppose that the maker of our candy machine claims that the proportion of orange candies is indeed 0.5. In a simple random sample of 100 candies, what is the probability that the proportion of orange candies is greater than 0.6? Would you consider this unusual or surprising? That is, if you took a sample of 100 candies and the proportion of orange candies were 0.6, would this be considered unusual? I'm going to show this first example using the z-score method, and then I'll use technology. And after this one, we're just going to use technology. So step 1, we need to check what I'm going to call the count condition. So N times P bigger than 10 and N times Q bigger than or equal to 10. And we take N, we have 100 times 0.5, that's greater than or equal to 10. And again, it's the same thing. P equals Q in this case. They're both bigger than 10, of course. Check the 10% condition. We're assuming the sample size of 100 is less than 10% of the entire population of candies. And because these two conditions are met, we can assume that the normal distribution can approximate this sampling distribution of P hat. So step 2 is to draw the normal curve. So I'm going to sketch that in up here. So the mean here is going to be 0.5. I'm looking for greater than 0.6. So we'll put that here. And the standard deviation is going to be, and I believe I've already worked this out, square root of P times 1 minus P over N, 0.5 times 0.5 over 100, and take the square root of that, and you get 0.05. And I'll often write that right below. Okay, step 3, look up the corresponding z-score. So we're looking for 0.6, so we convert that to a z-score. We're looking for where is z greater than 2. Again, we're looking for this value right here. So we look up 2.0. So we subtract this 0.47725 from 0.5 to get 0.022. So yes, this would be surprising. Our threshold, again, is 0.05, somewhat arbitrarily set, so it would be considered unusual. Okay, when I'm using technology, the only thing that's going to be different is that I'm going to use the TI-84 to crunch out the last part. I still have the graph drawn, and as we've seen before in other examples on the normal distribution, I put in the lower bound, upper bound, lower bound of 0.6, upper bound 1, e to the 99th, the mean of 0.5, sigma is 0.05, and then I paste that in, and I get 0.02275. Our threshold for determining if it's unusual or surprising is this value less than 0.05? If it is, we consider it unusual, surprising, and 0.02275 is less than 0.05. So yes, it would be considered surprising to get a sample proportion of 0.6 if indeed the population proportion were 0.5.